Hello, Weather and Forecasting Module 4. This is part 4. And we had an interlude with the little whiteboard page that I could show you how to utilize the curve. And so now I'm going to skip over and go back to kind of explaining terms again. And so if I have supersaturation, and you hear that term, it means that I have very small droplets that are liquid, or they can be solid, but they're at 200%. They're just not sticking together or becoming large enough for gravity to pull them down to the surface of the earth, which means that if I give something under supersaturation something to stick to, and that process of getting water to stick to itself is a hygroscopic process. If I give it something to stick to, that material that it sticks to is called a condensation nuclei. Now, there is another nuclei. It's called an ice crystal nuclei, and that is one that when the water sticks to it, it becomes solid as opposed to being liquid. So if the aerosol or the solid particle that the water droplet sticks to it and is liquid, I call it a condensation nuclei on the particle. If when the water sticks to it, it becomes solid, I call it an ice crystal nuclei. Both of these are known as heterogeneous nuclei, which means that as a water, it has a dissolution within the aerosol, so it becomes encapsulated in the aerosol. Here is a curvature just showing you the size of a water droplet. And one of the big misnomers of people with water droplets themselves is, what does a water droplet look like? And we'll talk a little bit about precipitation and precipitation process and what water droplets look like. We're just going to continue on with some of these terminologies. As far as condensation nuclei are concerned, they can consist of materials such as dust, salt particulates in the atmosphere, and ash. This is why when a plane goes flying by and it puts out aerosols out the back end of its tailpipe, you will sometimes see water condense on the aerosols, creating a contrail in the atmosphere. They are making a cloud. When I see a lot of persistent contrails, so a plane flew by maybe an hour ago, but I still see the line of where the plane flew by, that tells me that the atmosphere is incredibly moist up there right now. There's a lot of humidity in the atmosphere, in the upper reaches of the atmosphere, because I can see that the aerosols that I left behind from the tailpipe of my plane has created a lot of condensation material sticking to those aerosols. One of these effects goes back into that curve, the relative humidity curve, right? So this is my saturation humidity, and this has to do with droplet radius. The greater the saturation humidity, the bigger the droplet can be, right? I tend to make bigger liquid droplets if I have a lot more water present. Kind of makes sense, right? Ice crystal nuclei gets into a process called supercooled water droplets. So water droplets in the upper atmosphere are very, very small. They are microscopically small. Because of that, they do not have enough material in their existent form to act like a solid. This is actually a problem. If I don't have enough of the molecule to make it create its structure, its solid structure, I can't have it act like a solid. This is a problem that creates a liquid material that we call supercooled water droplets. These are water droplets that are much, much colder than actual solid should be. So they are below 0 degrees Celsius. They're actually typically averaging around negative 15 degrees Celsius, and they are still looking like or acting like gas. And this is because there's not enough material present for them to create a solid structure. But if given a condensation nuclei, in this case an ice crystal nuclei, for them to form around, they will become or create or have enough molecules to act like the solid structure they should be. When they are these cold gaseous materials, I call them supercooled water droplets, and that is their scientific name. So that's That's one of my most favorite science terms because it's just so dorky. Supercooled water droplets. They're around negative 15 degrees Celsius. This brings me to getting into adiabatic and diabatic processes. These diabatic processes are processes with which I can meet dew point temperature. And they follow the second law of thermodynamics, which you can read on above. It's basically saying that when given enough, it will come out of suspension when temperature is cooled, right? And that material will spontaneously move from hot source to cold sink. So I'm trying to create equilibrium between my hot sources and my cold sinks. Yes? Adiabatic process. This one I'm going to get you some images on, and I'll go into this in greater detail. But once again, terminology, so that when I show you the images and start to work sort of the math and numbers and how do we unlock this information, when I get into how to unlock that information, I want you to see these terms and know these terms. So adiabatic process is the process that when I take this moist air and it tends to be a little bit warmer than the air around it, it is less dense, and therefore it will begin to rise. As it begins to rise, if the water is not saturated, so it's not super saturated, if it's not at 100% saturation, or I haven't reached saturation specific humidity or my saturation mixing ratio, all the same terms, right? I'm throwing these terms at you so that we have them all the same. If I haven't met that line on my curve, I know it as a dry adiabatic lapse rate. The act of this material rising is known as the lifting condensation level. That is the level with which I will hit that line. So if my air molecule is moving up and it is simply just a specific humidity or a saturation, my saturation humidity in its location, right? It's just the amount of water. As it rises up, it will eventually cool off and meet its dew point temperature. When I hit my dew point temperature, I've hit what's called my lifting condensation level. This is the temperature with which my cloud forms. So if I want to know where the bottom of my cloud is, that is my lifting condensation level. Once I hit that point, all the rest of the cloud that forms above the base of that cloud is in what's called the saturated adiabatic lapse rate. This is the temperature with which the cloud itself is cooling off versus the air around it. As we know, down in the troposphere, the temperature cools down as I increase in altitude. So I go up, temperature gets colder. The temperature with which it will get colder is pretty consistent. This is known as my environmental lapse rate. If I take a parcel of air that's unusually warm and rising quicker, it will cool off at a dry adiabatic lapse rate. Once that parcel of air hits its dew point, it will start to form cloud material, or water will come out of suspension as those liquid droplets go from their state of more activity to a state of less activity. They actually warm up the air molecules around them. So they are releasing heat energy, and all the little nitrogens and oxygens floating around those little water molecules are gaining energy. And so instead of cooling off at a dry adiabatic lapse rate of 10 degrees Celsius every 1,000 meters, or 1 degree Celsius every 100 meters, it will begin to cool off at 0.5 degrees Celsius every 100 meters, or another way to think of it is 5 degrees Celsius every 1,000 meters. And that is known as my saturation lapse rate. The reason why it's cooling off more slowly, not as quickly as when it was dry, is because of the latent heat process, where my water molecules are going from their gas state into liquid and solid particles, and that is slowing it down or warming up the air around it. I know this all sounds confusing. I will give you images in my next video set.